and begin. Okay, so today our topic is Bootstrap. Okay, so on Monday we covered randomization tests, and with randomization tests, the idea was the treatments have been randomly assigned, and so any other arrangement of treatments would be equally valid, and we can set up, we can simulate our sampling distribution by redoing kind of the random assignment, shuffling up the random treatments and recording the measurements as such. Okay. Again, the kind of the key idea behind all of our statistical inference is that in our mind we have an idea of what the sampling distribution is. Okay. In Stats 10, your sampling distribution is based on the central limit theorem. We said when you take a bunch of samples of the mean, the central limit theorem says that sampling distribution will have a normal shape, and because it's a normal shape, we can do inference. On Monday, we saw randomization tests, and we said we can generate a sampling distribution by assuming that the assignment of treatments is random and exchangeable with any other assignment of treatments. And so with that, we are able to, under the null hypothesis, kind of break the association between the assignment of treatments and the values that we've observed. Okay, and we can create our sampling distribution under the null hypothesis, and then compare our observed sample versus the sampling distribution to see if our observed sample is something unique. Today we're going to cover Bootstrap, and Bootstrap is just another resampling method that allows us to create a sampling distribution. It's just here the assumptions are a little bit different. Random is again in your intro stats, the assumption is the central limit theorem applies. Randomization, the assumption is there's exchangeability. Okay, and Bootstrap, we're going to look at two different kinds of Bootstrap today. Maybe we'll only have time for one of them. I don't know. We'll see. Okay, there's two kinds of Bootstrap that we'll mention, and they make different assumptions about the population. And again, the key is we're trying to generate a sampling distribution based on this, what we're assuming to be true about the population. All right, so bootstrapping comes from the phrase, you know, pull yourself up by your bootstraps. And I tried to look this up because this is what somebody told me, and I said, well, is that really true, right? You should always kind of, whenever someone says something, you should kind of try to do some fact checking yourself. So I tried to verify this. I couldn't verify it, but there is like some idea that maybe this is one possibility of where the term bootstrap, pull yourself up by your bootstraps, comes from, and it's the that there was this German folk hero. He got stuck in the swamp, and the way he got himself unstuck was he pulled himself up by his bootstraps. Okay, it's a ridiculous idea, but it's the idea that you are helping yourself out without external help. Okay, you're getting yourself out of a problem without any kind of external help. And so the idea here is we call it bootstrapping is because we're going to generate a sampling distribution without any external help. Other than the sample that we have ourselves, we're not going to gather more data, we're not going to have access to the actual population. We're going to try to get a sampling distribution based on just our sample itself. Okay, and we have kind of two ideas. We've got parametric bootstrap, and we have non-parametric bootstrap. So that's kind of where we are now. Okay, so with parametric bootstrap, we're going to make assumptions about the population. Okay, so specifically, we're going to just say the population follows some particular parametric distribution. So probably the most kind of common example of this is you're going to say, well, I'm going to assume the population is normal. And on top of that, I'm going to assume that the mean of my population is equal to the mean of my sample. And I'm going to assume that the standard deviation of the population is equal to the standard deviation of my sample. Okay? These are obviously slightly dangerous assumptions. Okay? And obviously, if you're going to assume that the mean of the population is equal to the mean of your sample, you're not going to be able to make inferences about the mean of the population because you're just assuming it to be the mean of your sample. But you can still take this assumed population to then make conclusions about maybe two different samples and things like that. Okay, so it's still going to give you an idea of the sampling distribution, just certain properties of it, because we've made these big assumptions about the population. We can't make conclusions about them, right? So anyway, we're going to assume that the population is some distribution, whether it's the normal or some other distribution. Maybe you're going to assume that the population is chi-squared or Poisson or whatever it might be that applies to your situation. This is obviously going to take some, I guess, statistical intuition, right? Normal distributions make sense for continuous variables and things like that. And, you know, but you might say, well, maybe it makes sense to use a Poisson distribution. And when do we use a Poisson distribution?
Time.
And what about time? So the classic example for Poisson distribution is what? The number of customers in a line, right? Number of customers that appear in a line at the bank or something like that, or number of phone calls that come in within a certain interval of time. You guys are nodding your head like, oh yeah, I remember this, right? And then you have other distributions that you'll have to like look at the situation and say, this, like if we're going to try to model the number of phone calls that come in within an hour at the call center, then we could say, oh yeah, this makes sense to kind of assume that it's going to be Poisson. Or maybe it makes sense to assume that the time between calls would be what distribution? What's that? So the time between calls should be exponential, right? Exponential would mean lambda. Okay, so maybe some of you have to review your 100A, 100B stuff, but we have some kind of idea of what kind of distributions make sense and things like that. So so anyway, that's what we do with the parametric bootstrap. You assume that in this situation, this parametric distribution applies. I don't know why I'm getting all this static here. All right, sorry, we're just gonna have to live with that. Okay, we'll just pretend it's the rain. And then we generate a sampling distribution based on assuming what the population looks like. We generate a sampling distribution, and now we are able to compare our particular observed sample to the sampling distribution and say, is that my sample unusual under this assumption or not? Okay. Non-parametric bootstrap, and this is when people talk about bootstrap, they refer to non-parametric bootstrap in general, okay? Non-parametric bootstrap does not make any kind of parametric assumptions about the population. It's just going to say, here is my sample, and let's do the best we can with this. I'm not even going to assume that the population is normal. I'm not going to assume that the population is exponential or Poisson or whatever it is. We're going to just assume that I've got a sample that was obtained randomly from the population. That's going to be your big assumption, that your sample was obtained randomly. And we hope that's true because everything kind of relies on this random thing. And the kind of the heroic assumption of non-parametric bootstrap is if my sample is a random sample from the population, it is therefore representative of my population. And if it's representative of my population, if I want to create a population, I can just take my sample and clone it like a bajillion times, and now I have this kind of pseudo population which just consists of clones of my sample. Okay? This is going to drive me nuts, and I've got 2 hours of this. So anyway, that's what we're going to say. We're going to say I can take my sample and clone it like 1,000,000 times, and now I have the population, right? So it's kind of just like you did a random survey of 1,000 Americans or something, and then you're going to just clone that like whatever 300,000 times or something, and now you have a 300 million person population or something, and that's going to stand in for what the population of America looks like. Now, obviously, if your sample is not representative, then this is going to be a problem. But you're hoping that because you did a random sample that it should be representative, and we're going to generate our population this way. Okay, and then now that we've generated a population just by cloning my sample, 1,000,000 times, I can now draw directly from that simulated population and generate a sampling distribution. Does that kind of make sense? So we're taking our sample, we're just going to clone it a bunch of times. We now have this big population, quote unquote population, and then we just draw from that to get our sampling distribution. Okay? Turns out you don't actually even have to do the process of cloning your population, you're cloning your sample. You can just sample from your sample with replacement. Okay, so if you draw from your sample with replacement, that's effectively creating infinite copies of your sample to create your population. Okay, so that's what nonparametric bootstrap does. Okay, we sample from our sample with replacement, and that's effectively making infinite copies of our sample as our population, and we're drawing from that to create our sampling distribution. Is that okay? The idea there? And then once you have your sampling distribution, then you go and you make conclusions about your sample versus the sampling distribution. Okay? So these are parametric bootstrap and non-parametric bootstrap. These are just ways to create a sampling distribution so that we can take our observed sample, compare it to the sampling distribution, and make conclusions about whether our hypothesis that we use to create our sampling distribution is valid or not. Okay, so this might sound very similar to the randomization test, and what's the difference? Okay, so it's all comes down to kind of the assumptions that you are making about what your population looks like, or where your data is being generated from, right? So if the data you have came from random sampling from the population, then you can use nonparametric bootstrap, because you're good. The random sampling allows you to kind of then say, it's a little bit of a dangerous assumption, but you're going to say, well, because I got my sample via random sampling, I have to at least hope that it's representative of the population. Okay, so I'm going to go ahead and do bootstrap. If the data came via random sampling, and on top of that you're willing to make assumptions about the shape of the population, you can do parametric bootstrap. You're going to say, my data came via random sampling, therefore, because when you make parametric bootstraps, you're going to have to assume certain parameters about your population. So you're going to say, I'm going to assume my population has this mean and this standard deviation or this lambda term or whatever it might be. And so you're going to say, because my data came via random sampling, I have to at least be able to hope that my parameter estimates are representative of the population. And on top of that, I'm willing to assume the population has this specific distribution. I'm willing to assume it's Poisson. I'm willing to assume it's normal. And then you can do parametric bootstrap. Okay. On the other hand, if you have an experiment, okay, in general with an experiment you do not have random sampling. You have, you've obtained some participants that are not a random sample of the population. So you can't make these assumptions that Bootstrap does. But instead you have random assignment, and therefore you have exchangeability, and you do a randomization test. And again, in all of these cases, we're creating a sampling distribution based on kind of the different ideas behind the random process that generated our data. Yes, question?
When are we willing to assume the population has a parametric distribution?
It's going to depend on your statistical expertise. So when is, you can't just take data and say, oh, this is it, right? You have to kind of understand where the data came from, right? So if the data is coming from, this traditional example of like how many customers walked into the bank and waited in line, you might say, well, this is, my textbook Poisson distribution thing. And you might be able to make assumptions. In another situation, you might have something, I don't know, a little bit different, and you might have, you'll make other kind of assumptions, right? And so if you're willing to make these assumptions because you say, well, I paid attention in all of my stats classes and I understand when these distributions apply and I feel comfortable using this, then that's fine. If you're a little bit uncomfortable with doing that, then you might have to go the non-parametric route, but you're making a different assumption. You're going to say, I'm assuming my sample is representative of the population, which comes with its own drawbacks, right? So I don't know. The answer is it depends. So when is it depends with what you're comfortable with. Yeah. But that's kind of where we are. Oh gosh, look at this wall of text. This is just because I copied something out of our textbook. So anyway, we're using this textbook Ziefler called Comparing Groups. I think I've got a link to it in our syllabus. So when you do your homework, I reference that. Make sure you go to the appropriate textbook. Don't use the wrong textbook and wonder why the problem doesn't make sense. But where is it? So Comparing Groups. It's available free via the link. And we're doing randomization this is chapter 7 is the bootstrap, and I bet somebody forgot to turn their mic off and they're like hanging out in their office, and I don't know, that's my guess. Okay, so what this is what we're going for. Okay, we have this file called Latino Ed, and this was a study done in 2006. So I guess that's 13 years ago, and this comes from the 2000 census data. So 2 decades old now. But basically, the idea was, in the United States, we have a lot of immigrants coming from Latin America, and a lot of those immigrants come from Mexico, and the researchers were interested in for these immigrants who come to America, how far do they go in their schooling? Okay, do they complete high school? Do they go to college? They have these questions because education is highly correlated with a lot of other social things, and and wealth and all that. And so the researchers were interested in kind of the educational achievement of immigrants from Latin American countries, and they kind of wanted to compare is the educational achievement of immigrants from Mexico different from the educational achievement of other Latin American countries, so non-Mexico. Okay, and so anyway, they took a bunch of census data, and this is the study that they're curious about. Okay, that's what basically all of this says. The data has these what do you call it? Variables. Okay, and so we have the ID number of the person. Apparently, we're only looking at 150 people in this data set, which is a little bit smaller than what I would like. But this is, I guess 150 Latino immigrants from Los Angeles, and unfortunately, they don't tell us what the numbers actually mean. Okay, they have some kind of educational achievement level which ranges from 1 to 100, and with higher values referring to educational achievement. Unfortunately, we have no context. The data file that we have, at least coming from the textbook, and maybe if we dig into the actual articles and all of this, maybe we can figure out what these numbers represent, but we have no idea whether what a 50 represents. Is that graduated from high school, or is that like got to at least 10th grade in high school? We don't know. Okay, so that's the unfortunate thing. But somehow they were able to take this survey information, they coded it into numbers into our data set. Okay, and then there's other things. The year in which the immigrant arrived in the United States, the immigrant's age at the time of immigration, is this individual fluent in English, and did the individual come from Mexico? Okay, and so we're really just interested in the achievement versus whether they came from Mexico or not. Okay, that's as far as we are going to go. Okay, and so this is just kind of the first couple rows of our data set, and we have achievement level 59.2. Again, we have no idea what that means, and then whether they're from Mexico or not, and we have ones and zeros. Okay, so this is what our data set looks like. And so so here I can just do some dplyr, and I'll just say, give me the mean and standard deviation. I probably should have done count as well. Okay, I'll have to update that to get the count as well. Okay, and so 0 being immigrants not from Mexico, their mean educational achievement level was 64.5, and for the immigrants coming from Mexico, their mean educational achievement was 58.6, and these are the standard deviations. And the question is this number, 64.5, is that significantly different from 58.6? Okay, and it's hard to tell. We can't just look at it and guess. This is, okay, I don't know why this is being overlaid here, but this is a box plot of kind of education achievement levels for immigrants from Mexico versus non-Mexican Latin American countries, and this is kind of what it looks like. And anyway, the question is, is the mean level different? This is the median, but the question is the mean level different? If we create, okay, I have no idea why this shows up here. If we create a density plot overlaid on top of each other, this is the blue represents Mexico, and then the orange is other Latin American countries. This is what we have. I don't know. I don't know what the answer is. Okay. So, oh, it got cut off. Well, we still get a p-value. Okay. So the traditional analysis is we're going to make a t-test. Okay. And when you do a t-test, what kind of assumptions are you making?
Normal, but we don't know standard deviation.
Okay, we're going to assume that the sampling distribution is normal, but we don't know the standard deviation. And if we do a two-sample t-test, one of the other assumptions is that we're assuming that the two populations have equal variances. Okay, you can do a Welch test, which does not make this assumption, but we do this, and our null hypothesis is that the mean education achievement of Mexican immigrants minus the mean education achievement of non-Mexican or other Latin American country immigrants, that difference is equal to 0 versus the alternative that it's not equal to 0. Okay, and again, we saw from our summary that there is a non-zero difference in our data, and when we do the p-value, we get something just under 5%. We get 0.04597, and so depending on what level alpha you are choosing, you might say this difference is significant if you're using 5%, and if you're using something less than 5%, you're going to say it's not significant, okay? Using a traditional t-test. Okay, so this is where we find ourselves now. All right, so now we'll talk the parametric bootstrap and how we would do the same kind of test under the parametric bootstrap, okay? So what we want to do is we want to create a sampling distribution of this quantity, the sample mean of Mexican immigrants' mean educational achievement level versus the sample mean of other Latin American countries. And again, our null hypothesis is that that difference is 0, okay? And again, if we're going to assume that the variances are equal, this null hypothesis effectively states that the values we have obtained in our data come from the same population. Okay, if we randomly selected our sample, that the scores for, or the education achievement levels for the Mexican immigrants and the education achievement of the other Latin American country immigrants, those things are coming from the same population, okay? That they have the same mean, they're coming from the same population. So that's what we're going to use to generate our parametric bootstrap data. So we're going to say both groups come from the same population. So, sorry, again, this is getting cut off. We're going to see we have a total of 150 people. Of those, 116 came from Mexico, 34 came from other countries. And then in the summary, well, it's this same summary data that I had earlier. But I'll go ahead and run everything above this page. Okay, run everything else. Oh. Is everything okay? I hope. I'm sorry that something happened. Maybe we spilled a drink. Okay. Well, that's the most excitement we've had all day. And so what we do is we can just calculate the difference between 64.5 and 58.6, and that difference is 5.9. Okay, so is this difference that we observed of 5.9, is that statistically significant? And so to get our p-value, we're going to say, what is the probability of observing our data or something more unusual, meaning what's the probability that two randomly drawn samples have a difference of 5.9 or more, the absolute value, I should say, because it's a two-sided thing, if both samples are drawn from the same population, okay? And so that's what we're going to do. And so the population that we're going to create to simulate our population thing is that we are going to assume that the population is normally distributed. Maybe this is not a good assumption, okay? That the population, that the scores of education achievement we're right now assuming is normal. Maybe that's a bad assumption, okay? And then the other thing is we're going to use our data set's overall mean, the mean of all 150. So that's going to be all immigrants from Mexico and other Latin American countries kind of pooled together, and that's going to be the overall mean and the overall standard deviation. Those are going to be the values we use to simulate our normal distribution. And so this is what our code is going to look like. For reproducibility, I'm going to set a seed of 200, whatever. Okay, I'm going to do this 10,000 times, and I'm going to simulate for Mexico and other countries. We just use our norm, and both of these things have the same mean and same standard deviation. So we're going to use the M comes from the overall, the mean of this entire column. This standard deviation comes from the standard deviation of the entire column. Everybody pulled together. We're going to use these two values to just define our normal distribution. Okay, so we're just simulating a normal distribution with this mean and this standard deviation for everybody, and just to kind of recreate the same sizes of the samples that we have, we're going to say 116 forms are kind of our simulated values for Mexico, and 34, our norm 34, will create our simulated values for the other countries. Okay, and so this is what we do, and then we're going to calculate the mean of this simulated sample, the mean of this simulated sample, and take that difference and record it. Okay, and so this is going to produce a whole bunch of differences between the two groups if we're going to assume that they come from the same population, which is what our null hypothesis states. Okay, but again, the big assumption here is that the population is normal, which maybe that's a bad assumption. Okay, I mean, we can look at this thing. So you look at this thing and you say, well, could the population be normal and generate this thing? And I don't know, okay? I guess. We can't avoid having to make assumptions. That's the whole idea of statistics, is what assumptions can we make? Is it safe to make these assumptions? And things like that. Okay, so we will calculate our empirical value by taking this vector of differences, and we're going to say how many of those differences have are greater than or equal to our observed difference. And it turns out this happens 0.0453 out of, so I guess 453 times out of 10,000. Okay, so about a little bit under 5%, which lines up quite closely to what we got over here. According to the Ttest, we would get 0.04597. So our parametric simulations agree with that. Okay, and as we would expect, because basically that's what those are like the same assumptions that go into a T-test. Okay, and so.
So are we using the mean standard deviation of the sample that we got?
We're using the mean, yeah, the mean of our sample and the standard deviation of our sample, and we're using that as, we're going to assume that the mean of the population is equal to our sample mean, and the standard deviation of our population is equal to our standard thing. Okay, and so obviously we could not use this and then ask, is the could the mean of the population actually be this value over here? Okay, because it's like saying, well, if you're going to assume the mean of the population is this, can we then conclude that the mean of the population is this? Well, that would be a terrible thing to do, because what we've done is we're assuming that the mean of the population is something. So it doesn't make sense to do some kind of thing like that. But this is useful in helping us understand the sampling distribution of what kind of values would we get for two random samples and their differences. Okay, so what kind of distribution will we get if we take two random samples and we take their difference? That's not as intuitive. I think you guys learned this in 100A or 100B, where you learned that the difference of two randomly distributed variables is itself a randomly distributed, two normally distributed variables. The difference between them is going to be another normal distribution where the mean is mu A minus mu B, and the variance is variance of A plus the variance of B, things like that, right? So I think you guys learned that, but anyway, that's basically what the t-test is assuming here. Yeah, question?
Is the number 116 and 34 the number of population?
Yes, so back here, we counted how many in our sample are from Mexico and how many in our sample are not from Mexico. And we have 116 and 34, and that's where our numbers are going. So we're basically trying to say, what if I drew another sample with this kind of same counts, 116 people from Mexico, assuming that they come from this normal distribution, and 34 people not from Mexico, assuming they come from the same distribution. Okay. So this is what we get, and we're going to compare our differences versus that. Okay, I think we're out of time to get into the non-parametric bootstrap. So we'll cover that on Friday. What I do want to do, and this is going to be my other time, we're going to do our manual roll call. So I'm going to